Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
Welcome to The Explainer. I'm absolutely thrilled to have you here today because we're about to embark on a truly fascinating journey. We're going to take the invisible laws of physics, the stuff happening on a completely microscopic level, and demystify exactly how they translate into the tangible, everyday reality of the devices we use constantly. If you've ever looked at a gadget and thought, how on earth does this actually work at a fundamental level? Well, you're in the exact right place. We're going to build this understanding piece by piece, logically and completely from the ground up. Okay, let's dive right into our roadmap. We'll start with Section 1, the magic of electrons. Then move to 2, current, voltage, and resistance. From there, we'll connect them with 3, Ohm's law and the hill. Next, we scale up to 4, circuits and electrical power. Check out the hardware in 5, power supplies versus batteries, and wrap the whole thing up with 6, basic electronic components.
Section 1, the magic of electrons, the basics. To kick things off and set a solid baseline, we need a really simple, clear definition of what it is we're actually talking about. So, what are electronics? At their core, electronics are just devices that move electrons around to accomplish a specific task. That's literally the whole shebang. Whether you're racing a remote control car, scrolling endlessly on your phone, or just flipping the light switch in your kitchen, you're essentially just commanding electrons to move. Every single electronic device you interact with is, fundamentally, just an electron-moving machine. Think about a classic model of an atom. You've got your protons and neutrons hanging out in the center, and those little negatively charged particles zooming around the outside? Yep, those are our electrons. The physical truth of absolutely everything we're discussing today is based entirely on manipulating these tiny little guys. Electrons exist within matter, and they carry a built-in electric charge. Because they sit on the outside of the atom, they're the ones that can sometimes break free and move around. And getting them to move in an organized, predictable way, that is exactly what makes all of our modern technology possible.
Section 2, current, voltage, and resistance, the 3 forces.
So how do we actually get these electrons to move? And more importantly, how do we control them? Well, it really helps to think of the mechanisms here as invisible characters. Personifying them just makes the physics so much easier to wrap your head around. First up, let's meet current. Symbolized by the letter I and measured in amperes, or just amps for short, current is the speed with which electric charge moves. Formally, it's the amount of charge moving past a specific point per second. You can think of it as the ultimate agent of change. If there's no current flowing, absolutely no change is happening. Nothing lights up, nothing computes. Current is the flow itself.
Next in the lineup, we have voltage, symbolized by V and measured in volts. Voltage is basically the energy used or gained by moving a charge from one point to another. It's a relative potential energy between 2 distinct points. A really great way to think about this is that electric charge is fundamentally lazy. It naturally just wants to flow down from a higher state of energy to a lower one, which we call flowing down a voltage drop. And because voltage is relative, we usually assign a specific reference point in a system that all other voltages are measured against. We call that ultimate low energy reference point ground.
And our third character is resistance, symbolized by R and measured in ohms. Honestly, you can playfully picture resistance as a bit of a thief. See, all materials have some built-in level of resistance. As our current flows through a material, that material steals kinetic energy from the moving charge and dispels it outward as heat, which, let's be real, is usually a massive nuisance when your laptop starts feeling like a frying pan. Resistance is literally the rate of this energy theft. To put it simply, it slows down current flow. It's the pushback against those moving electrons. Section 3, Ohm's law and the hill, connecting the dots.
All right, now that we've met our 3 main characters, current, voltage, and resistance, we're ready to put them together. The absolute crucial point here is how these 3 forces balance each other out mathematically. This relationship is captured in a famous, fundamental rule known as Ohm's law. It simply states that V equals I times R. In other words, voltage equals current multiplied by resistance. This one tiny equation quantifies the exact relationship between our 3 characters. And any devices or materials that strictly obey this linear rule, like your basic wires and resistors, are referred to as ohmic. There's actually a brilliant analogy that illustrates this whole concept, mapping these abstract ideas directly to physical things we experience every single day. Imagine a box sliding down a hill. The box itself, that represents the electric charge. Gravity, which is actively pulling that box down the hill, is our voltage. The velocity, the actual speed the box is sliding at, is our current. And finally, the friction between the box and the ground, which slows the whole thing down, is our resistance. Think about it. If you make the hill steeper, which means increasing the voltage, the box moves faster, so current increases. If you make the ground rougher, increasing the resistance, the box slows down and current decreases. It is just a perfect way to visualize Ohm's law. Section 4. Circuits and electrical power. Closed loops. With those foundational rules locked in, let's take a step back and look at the macro scale. Current doesn't just wander off wherever it feels like it demands a clear path. It only flows through closed loops, and we call these loops circuits. In any circuit, you've got active parts and passive parts. Active parts, like a battery, supply the power. They literally lift the charge up to a higher energy state, creating a voltage rise for the current to flow from. Then, the current travels through the passive parts, like a light bulb or a tiny motor, which consume that power. As the current moves through those passive parts, it flows down voltage drops, eventually returning right back to that 0-volt reference point we call ground, ready to be pumped back up by the active part all over again. And that naturally brings us to electrical power, which is the actual work getting done in our circuit. Power is calculated just by multiplying voltage by current. It represents the total energy being used every single second, and it's measured in watts. This is a massively important metric for anyone tinkering with electronics because pretty much all physical components have a maximum power rating. If you push too much power, too many watts through a part that just can't handle it, that energy theft we talked about will generate way too much heat, and you run the very real risk of literally burning your parts to a crisp.
Section 5. Power supplies versus batteries. Sources of power.
Okay, so we understand how power works inside the loop. But we have to ask, where are we actually getting this power from in the first place? What's really fascinating here is the stark contrast in how we physically provide that necessary juice to a circuit. You can use a benchtop power supply, the kind you typically find sitting in a lab or a garage workshop. Or you can use portable batteries, the exact same ones powering the gadgets in your pocket right now. Both of these are active components, providing that crucial voltage rise. But in practice, they behave incredibly differently. Let's break those differences down. Benchtop power supplies plug directly into a wall outlet. Because they draw straight from the main power grid, they are insanely safe, super reliable, and incredibly versatile. You get a totally steady, constant stream of power. Batteries, on the other hand, have to physically store their own energy chemically, which we usually measure in milliwatt hours. Whether we're talking rechargeable lithium ions or just classic single-use alkalines, their biggest advantage is obvious. They're portable. But they're generally a lot harder to design around. Their voltage actually drops over time as they discharge, and they have limited current delivery because of their higher internal resistance. So it's always this constant trade-off between the rock-solid reliability of a wall plug and the ultimate freedom of a battery.
Section 6. Basic electronic components. Building blocks.
All right, we've got our physics, we have our power sources, and we know our mathematical laws. Now think about the incredible variety of actual physical parts that go into these things. To the untrained eye, a pile of components just looks like a random assortment of tiny metal and plastic shapes. But these are the tangible building blocks of literally every electronic device on Earth. When you crack open a remote control or a radio, this is exactly what you see. Every single shape, size, and color represents a specific component that was engineered to manipulate our invisible friends: current, voltage, and resistance in very, very specific ways. Now, we're not going to deep dive into the complex physics of every single part today, but you absolutely should recognize the names of the heavy hitters. We've got resistors to deliberately slow current down. We have capacitors and inductors, which temporarily store energy in electric and magnetic fields. There are diodes, which act like one-way valves, forcing current to flow in only one direction. We have transistors, which act as tiny electronic switches and amplifiers, and of course, simple mechanical buttons to manually break or connect a circuit. Combining just these simple tools allows us to build absolutely anything, from a blinking LED light all the way up to a supercomputer. And just like that, our micro to macro journey comes to its tangible conclusion. We started with invisible electrons moving inside atoms. We met the forces of voltage, current, and resistance that boss them around. We mapped it all out perfectly with Ohm's law. And finally, we looked at the physical loops, power supplies, and actual components that make up real-world hardware. So, armed with this newly demystified foundation, what incredible device are you going to build first? The rules are clear, the components are out there waiting, and the possibilities are literally endless. Thank you so much for joining me today on The Explainer, and keep learning.